Okay, so welcome to the Qmmm modeling of enzyme reactions part of the CCPBioSim workshop. I understood that a lot of you have been going through a lot of the workshops this week, and with the absence of the first day with Python modeling, there has been a little bit of a challenge occasionally in some. So I'd like to set your mind at ease, first of all, that in this workshop, we don't really need to use any Python stuff. We do have an IPython notebook, which you could just run an occasional cell. If you want to do it completely without the IPython notebook, that's possible also. What we will do is run our own Qmmm simulation. Every one of you will do that, but we'll do that through the command prompt on the server. So just some simple Linux commands that hopefully most of you will be familiar with, and otherwise you can copy them from the instructions. So it should all be fairly straightforward. So what I will start with is a short introduction to Qmmm modeling. I'll promise to keep it short, and specifically the enzyme reaction that we're going to model during this workshop. So I'm Marc, by the way, Marc Kamp. Jida is a PhD student who's there in the corner. For those in the room, will be there to help when we start running things. Okay, so let me just see. So I'm going to start really basic, but I'll do it quickly. Enzymes, that's what we're going to look at. We're going to look at an enzyme, and they are catalysts. They lower the barrier of a reaction. So a standard reaction might look like this. From substrate to product, it goes over a barrier. But in an enzyme, we will have a substrate bind, and it will then go over its own barrier, which we expect to be lower, right? So that's the enzymatic barrier. So this part, from the enzyme substrate complex to the enzyme product complex, that is what we can model using a Qmmm simulation. And then, of course, we could compare that directly to experiment through standard Arrhenius equation, where we just compare that to the rate, for example, measured using steady-state kinetics. A bit more on how accurate that comparison is later. I think it's not always the key point of a Qmmm simulation should not be, oh, how close do we get to this kcat value? Usually you want to try and use it to answer questions. So for example, relative rates are much more important. Is this substrate converted faster by this enzyme, or is this enzyme variant better at catalyzing this reaction versus another? Okay, so this is a slide that I often put up for experimentalists as well, just to point out that the full enzyme catalytic cycle doesn't only involve the chemical step, which is this chemical conversion from substrate to product, but also substrate binding and product release. This normally isn't really dissected using experimental methods, and can be done, but it's tricky. With computational simulations, this is really easy. We normally use some MMND simulations for this first part, and some MMND simulations for this other part, or other methods that you've learned about this week. But for this chemical conversion bit, we need to go beyond standard molecular mechanics. So this is where the Qmmm comes in. The quantum mechanics part is then used for only a small part of your system. So typically a substrate and some key reacting groups in the enzyme. This is where the actual bond making and breaking happens, the changes in the electronic structure, and then the rest is treated using molecular mechanics. And we do this mostly for speed, because otherwise these whole enzyme systems would be far too expensive to routinely simulate. So this multi-skill way of modeling was essentially what won the Nobel Prize in 2013. And I've put a couple of reviews on this slide here. The first one came out well before the Nobel Prize was announced, but it sort of gives you an overview at a relatively high level of the methods as well as some applications. And then the other one underneath there is for actually much more in-depth discussion of all the different methodological parts that can be involved in Qmmm simulations. So now I'm just going to highlight a couple of key points. First of all, the trade-off between accuracy and speed when we talk about Qmmm. So this is really to do with what level of quantum mechanics we're using. Now, this will very much depend on your background. For some of you, this will be all gobbledygook or at least letter soup. But essentially, with what we've got on this scale here, this method, CCSD parenthesis T, is something that gives you essentially, it's a gold standard for standard organic reactions, so it gives you very, very high accuracy. But if we think about what we can do with this, we can't really afford, and especially not in a Qmmm setting, even to optimize a structure at that level. So what happens usually is that you will do an optimization at, for example, some reasonable DFT functional, and then you could do calculations at these high levels if you want. Most of the time, though, we're actually interested in doing a bit more sampling and a bit more speed, so then we can use a whole range of semi-empirical quantum mechanical methods, which tend to be like an order of magnitude faster or more than DFT methods. So then you can afford to do more sampling. It does come at the cost generally of accuracy. So these methods can really overestimate energy barriers, for example. I also put on here EVB. This is actually a very different thing. It can sometimes be classed as Qmmm, but you don't really have electrons there. But it is a method that is very useful for lots and lots of sampling, but you will need to parameterize it for a specific reaction. That's not what we're looking at today. We're looking at Qmmm methods where we're just taking part of our system, we treat it quantum mechanically using whatever Qm method we have of interest. Okay, so then apart from the speed accuracy choice, we can have to make some other decisions as well. You know, what is exactly in our Qm region? How do we couple the Qm and theMm region? And even on the standard Mn molecular mechanics side, we can wonder what's the best force field to use. Are we having periodic boundary conditions and so on? Normally, we don't have to think about that too much, and we won't be thinking about that in detail during this tutorial either. So I'm often saying that, you know, apart from those methodological choices, it's important also to think about what is easy to use. Can we easily now run a second simulation with a different enzyme or something else? And of course, what do you have available as computational resources? And with that, we should not only think about, okay, how long does my simulation take, but also how much time does it take me if I want to start running a simulation, such as the model setup, parameterization, and so on. So hopefully today you'll get an example of something that can be done with a really light touch and from the human side as well. So before I go into the specific application system of the day, I'll talk a little bit more about what we need to do in Qmmm. So we can't just say, let's treat the substrate and these groups in the enzyme quantum mechanically, and we run a molecular dynamics simulation and hope that we see a reaction happen. Because enzymes usually have rates of, say, 1 per second. We could never ever dream of sampling for that long, right? So we can't expect it to spontaneously happen. That is why we need to force the reaction to happen. We need to add something to the system to say, okay, I want to push these atoms apart and so on. So that's what we can call applying bias along the reaction coordinate. Now, the reaction coordinate can be defined in many different ways. We'll use a very simple description, which we'll go into later during the tutorial. We just need to make sure that we go along this reaction coordinate. Then I'm going to distinguish two fundamentally different ways of looking at an enzyme reaction. The first one is to look at potential energy surface of the reaction. So this is where we don't include the dynamics of the system. We're just going to take minimized snapshots along the reaction that will indicate our reaction. So we can use energy minimization in a Qmmm energy surface. So that looks a little bit like that. You can take points along your reaction coordinate. You can optimize one point. Once that's optimized, you move it a little step along your reaction coordinate and you optimize that point, and so on and so on. So you can do that step in a stepwise fashion and then get these different points. So you directly get the Qmmm energy directly from your simulation program, and that will give you a potential energy profile and the potential energy surface for your reaction. This is sometimes, and I really do say sometimes, called adiabatic mapping. I'm mostly mentioning that term because it's in the file names that you'll see later on when we do this approach. it briefly means that we're staying on the same potential energy surface, so we don't have a sudden jump here from one to the other. We like to keep this profile nice and smooth. Then there's another way where we will include free energy to model reactions. That can be using molecular dynamic simulations, but now with Qmmm. Then we're not taking energies directly from the output of the program, but instead we're going to sample a particular quantity along the reaction coordinate. So this could be, a bond distance and so on. So that sampling is called an umbrella sampling, because we will do it still on different points along your reaction coordinate. So we take a point along our reaction coordinate, we put some restraint on a key distance, and we sample around it. That's where the umbrellas come from. So they don't really look like umbrellas here, but these are essentially histograms of the distribution of what you're sampling at that point. And then you can move on to the next point and you do the same type of sampling. So what we're gathering there is effectively statistics of your measurement of interest, say your bond length of interest, when you have a particular restraint on this. And then later we can unbias that using, for example, weighted histogram analysis methods is very popular for that. So when you unbias that, you get an energy profile, a free energy profile. And essentially what this means is that when the line is going up, when you're going up in energy from one to the other, you expect there to be more sampling on the low energy side than on the high energy side if you sample along there. So that's very briefly how that works, right? And then on the other side, you'll sample more to the right than to the left if you sample with the restraint around here. That bias, that information is what we use to get this free energy profile. Okay, so I'm mentioning these techniques in some detail because we'll do both of these during our practical, and we'll be using the additive approach. I'm not going to stay long on this slide. Additive approach essentially just means that we've got our energy for the Qm region, energy from the Mn region, and we've got an interaction between the two, which contains both electrostatics and van der Waals interactions. The van der Waals interactions in this kind of scheme are actually treated at an Mn-like level. So we still, in our Qm region, we use some little bit of Mn for this Mn interaction, but that works perfectly fine. There's also a subtractive approach. We won't go into much detail now. That's essentially, if people are used to using Gaussian, for example, the Ohmian method that's implemented in there. If you do end up using this at some point, this subtractive approach, then it's particularly important that you take care that you are using what is called electrostatic embedding, so that your Qm atoms feel the charges of your Mn atoms, because that's, for any enzyme reaction, really, really important. That's automatically included when you use an additive approach. Okay, so then one thing that is often used in enzyme reactions, not in the one that we use today, but often you will have groups in your enzyme, what I mean is amino acid side chains that are involved in the reaction. Right? The base, for example, very common, sometimes you get a nucleophilic attack. Then you will need to include those in your Qm region. But of course, then you're going to come across a bond that crosses your Mn and your Qm region. So we need to do something there. And there are some common approaches to do that. And I'm mostly focused here on this link atom approach. So what we need to do there is we have a Qm atom that doesn't have a satisfied valence, because its bond is then combined with an Mn atom, and there are no electrons on that Mn atom. So we either need to pretend that there are some electrons on the Mn atom, that's this Frozen-Hibbert approach, or, and this is a very flexible approach and therefore implemented in a lot of software, including the Amber way of doing Qmmm, and that is having sort of insert an extra atom that will act on the Mn side for Mn calculations and on the Qm side for Qm calculations, that you constrain along this bond between the Qm and the Mn atom. So we call that a link atom. When you run this using Amber software, you don't even have to worry about that. It will insert link atoms completely automatically, and that works absolutely fine. Okay, so this slide I'm really not going to talk about much. I'm just saying quantum mechanical modeling. That's what we're doing. I already mentioned some different flavors of Qm. So here are some names that you might come across in this tutorial, or when you read some papers where they use Qmmm. We have semi-empirical methods that are really fast, so we can easily do some Qmmm-ND. We can have ab initio methods, Hartree-Fock. It's not accurate, but the other methods can get really accurate, but also will get very slow. And then we've got density functional theory with some common functionals here that you might come across. And that works reasonably well, but if you want to do Qmmm simulations, then it is going to cost you more because they are a lot more expensive than semi-empirical methods. Okay, so we're going to look at an enzyme-catalyzed reaction in the workshop, and we're going to actually do some analysis of that. So these are all things that we can do in principle with Qmmm reaction modeling. We can determine the mechanism of a reaction. That's mostly done by following both different mechanisms, or all the different mechanisms that you think are plausible, and seeing what the relative energy barriers are. It's like, okay, this is clearly the lowest energy barrier, it must be this. We can also identify intermediates, catalytic residues, and so on. We can analyze contributions to catalysis. So what is really important in this enzyme to catalyze the reaction, bring down the chemical step. We can explore conformational effects. At a very simple level, we will get a little movie of what your reaction in the enzyme looks like. And that can sometimes already be quite useful for yourself to just get this visualization. And that helps then to relate enzyme structure to activity. So with what we do in the tutorial today is where I've put arrows. So we will also analyze the contributions to catalysis in this case. And we will be looking at Chorismate mutase, an enzyme important to make aromatic amino acids in bacteria and so on. We can't make it ourselves. That's why we need to get it from our food. If you're interested in chemistry, it's Claisen rearrangement reaction. The reason why this is popular, or has been popular, with Qmmm methodology and testing and so on, and even sort of the original debates of why is an enzyme reaction so much faster than a reaction in solution. This has been a very popular reaction because the mechanism is exactly the same in the enzyme as it is in solution, as it is anywhere else. And that's because we have a reaction that is simply one bond that breaks, carbon-oxygen bond, and one carbon-carbon bond that forms. And in the transition state, we expect to see both of these bonds half broken, half formed, whichever you want to call it. So that's the highest point in the reaction. Okay, so very briefly, what the structures, how I obtained the structures that you'll be starting with when we run our simulations. So we've made a tool a little while ago, which is called Enlighten. That is a plugin to Qmmm. And it's also an automated way to just set up an enzyme ligand system without you having to think about parameterization too much. So this is really crude depiction here. What I'm indicating with this Enlighten depiction is that we are the way that we keep things cheap to actually run some simulations in your Qmmm session on your own laptop is by only using a sphere of solvent, and inside is the ligand, and then outside we keep everything fixed. And so that's sort of an efficient way. And then this is a picture here made after the setup of this in Qmmm. So the enzyme we look at, Chorismate mutase, is a trimeric enzyme. So we're going to focus on just one active site, and we've solvated that one active site. The other water molecules are there just from the crystal structure. Not going to stay long on this, but if you wanted to try and replicate something like this later, or do it for your own system, then you can just use this Enlighten plugin, and the only things you need are an installation of Qmmm, and you need to have Docker running in the background. All the information is on the website if you do want to do this. This is just to show that there's, in the gray box, a bunch of stuff happening in the background that you don't need to worry about. You just have a few simple menus where you click, I want to prepare the system, or I want to run dynamics. That's what you'll see as extra windows in your Qmmm session. Okay, so then the preparation outcome for this. So I took this crystal structure of Chorismate mutase, where there is a transition state analog in the active site. The only thing I did to that is I just modified the atom so that it's the actual Chorismate substrate rather than the transition state analog, just by changing that in PyMol. So no optimization, and this means that this bond is still too short because there is no bond here at this point. Then we run sort of the automated prep through the Analysing plugin, which just takes about half a minute. That means that everything is protonated. We've got additional solvent added and so on. Then we can relax the structure a little bit, after which you'll see that Chorismate adopts a more normal conformation than we expect. That just takes a few minutes. This is on a pretty slow laptop. Then we can run some dynamics, and this is partly why I've done this before the workshop. So just 100 picosecond dynamics still took about 40 minutes, or probably if I'd run it on this, it would be more like 30, 25. And then from that point, this is where we're taking it now at the workshop. I've saved 20 different snapshots from this short dynamic simulation. You can each pick one of those and use it as your starting point to run a Qmmm umbrella sampling calculation, such as the ones shown here. And again, we'll be using something similar to on the cloud to what is used here. Actually, it's a bit faster, so expect that this first step is going to take you between 15 and 18 minutes, something like that. So once we get to that point in the workshop, it's useful to make sure that you get that one running. So so then you can sort of get some coffee before it's 3 o'clock and the coffee place is shut. Okay, so Chorismate mutase reaction. As I mentioned, we need to force this. The way that we're going to force this, we're going to use geometric reaction coordinate. And our reaction coordinate, we know it works well in this particular case, is simply the difference between two distances. So it's the distance of the bond that's being broken, this one or this one, and the distance of the bond that's being formed, this one here in transition state, or this one. So by taking that difference, we expect that when we are still in the Chorismate place, then, what is a carbon-oxygen bond? 1.6 angstrom, something like that. This one will be 3.5 or more. I'm just going to talk a little bit to finish up our workshop session, looking at not so much exactly your results, but also how this same work has been done in the past and published at a slightly higher level. So this won't take half an hour. So after this, we still have time to finish your workshop if you haven't, or ask me any questions. So as the recording has started, I will start this now. So we've done Qmmm modeling of an enzyme reaction, and the enzyme reaction that we modeled was the Chorismate mutase reaction, the transformation of Chorismate to prephenate. By following this reaction coordinate, that was the difference in the bond being broken and the bond being formed. So the results from this, when we got to the adiabatic mapping stage, will look something like this. So hopefully most of you will have made this plot by now. So what we have here is, first of all, the energies that came out of our calculation directly, the Qmmm total energies, that's in blue. That has given us a certain barrier for the reaction, in this case, roughly 24 kcal per mole. That's higher than what we expect for the actual enzyme. That's just because we're using a semi-empirical method that isn't very accurate. But what we're interested in here really is how much work is being done by the enzyme. So we've calculated that by simply taking the exact points that we optimized inside the enzyme, but now throw away all the enzyme and redo the Qm calculation. So this is now what would the energy be for the exact conformations that are present in the enzyme, but without any of the stabilizing influence of the enzyme around it. That's the orange curve. Now there we see that the barrier is much higher. And in fact, the product is more stable than the reactant as well. So that means that what the enzyme is doing compared to this is that it's lowering the energy barrier. That's what we expect. It also happens to make the enzyme product complex a little bit less stable than it would be without the enzyme there, which is good because the product could lead to product inhibition of our enzyme. Then the final thing that was also automated to be calculated in the adiabatic mapping script is to simply take our Qmmm structures again, and instead of throwing the whole enzyme away, we only throw out the side chain of arginine 90. Now in this example, and this may be slightly different for your examples, what we see then is that the reactant and product difference, energy difference is approximately the same, but the barrier is pretty much as high as it is without any of the enzyme. So what this indicates is that this arginine is doing by far the bulk or almost everything of the stabilization of the transition state. That's one way we can use these simulations to do something that's non-chemical, right? Because we take the structures optimized within the enzyme and simply throw something out and do a recalculation. So this way you could calculate the influence of all the residues in your active site if you do that step by step. So the other thing that we've looked at and we were talking about is to see how high our energy barrier was and how much stabilization was provided by the enzyme. So that's the difference between the, in this case, the blue and the orange curve. Now I haven't collected all the numbers yet for people that have run it now, and I haven't received any on Zoom to have a slightly higher number, but we have done this before in a previous iteration where we used a slightly different semi-empirical methods, which is why our barriers are overall a bit higher. But what we see if we plot the energy barrier versus how much stabilization the enzyme has done, we do see a correlation there with reasonable correlation coefficient. Now this same work was done in the past when there were quite a few debates of what it actually is that an enzyme stabilizes during an enzyme reaction. So now we do here, what's being done is exactly the same as what you've done with adiabatic mapping. The difference is that a DFT method, then still very popular, it's becoming a little bit less popular. B3-lib was being used to generate, about 10 different paths. This is the Qmmm energy. This is the Qm gas phase energy. You can subtract the two from each other to get the stabilization over the pathway. And then you can plot those same points against each other. And you can see that there is a very good correlation in this case. So at that point, a while ago now, 2005, they could conclude that the correlation of barrier height with transition state stabilization shows that the efficiency of the reaction of the enzyme is determined by the degree of stabilization in the enzyme. They could go further later on where they've done the same thing, not only in the enzyme, so these are just the stabilization energies, but also in solution. Because if we want to compare this fairly, and we can do this for Chorismate mutase, we should also compare what water is doing. Because it turns out that water, just aqueous solution, can stabilize a little bit as well. Again, if you plot the circles here, this is the reaction in water, the triangles here, the reaction in the enzyme, that same correlation still holds. It's just that the water ones all have higher barriers and the enzyme ones have lower barriers. So if you take the averages there, these are now calculated with these B3-lib Qmmm calculations, we get a clear difference between enzyme and solution. We also have numbers from experiment. So this is for the enthalpic barrier actually. So that's something that's very close to the potential energy that we're calculating here. So you can see that agrees reasonably well, although in solution experimentally there is even a larger difference than we find here. Now there's actually a reason for that. So these numbers were calculated just from the rates of the reaction. There's a reason for that because in reality, if you do the experiment, the Chorismate is going to be most of the time in a different conformation than the one that was simulated because this one is more ready for the reaction to occur. So I won't go into too much detail here, but different groups using different methods have also calculated how much the contribution is of this equilibrium. How much does it cost? So the binding of what is then called the reactive pseudo-diaxial conformation, it's conformation B. So, you know, generating that contributes a certain amount as well to the free energy overall. And one thing to say here, so we have these different effects, the better transition state stabilization. We've got something like substrate compression when it binds to the enzyme, so there's a binding effect, and there is this conformational effect in the substrate conformation specifically that will be different in solution. So all of those effects are due to the fact that the enzyme environment, the enzyme active site, is built to stabilize the transition state. If you build it to stabilize the transition state, it's much more likely to bind this conformation of the substrate than this. So you can add that correction to the solution reaction. So depending on what process you use, you get sort of a range there. And then these values actually are quite nicely in line with what is found by experiment. There is, with B3 a slight underestimation. We can get to that in a moment. So the one other thing that I already pointed out earlier when with the viewing in VMD, we've got this arginine residue that is sort of perfectly placed to provide electrostatic stabilization when this carbon-oxygen bond breaks. So you get negative charge on the oxygen. That's that arginine 90. And here, the same calculation that you've been doing for arginine 90 was done, but also for several other of the active site residues based on the B3 Qmmm calculations. So yes, arginine is providing the bulk of the enzyme stabilization, but not all of it. Some others also have a positive influence on the stabilization overall. So that type of analysis you can now do using the same protocols that you use today. So it is possible to go to higher level methods, estimations of the barrier, and I won't spend too long on this. Suffice to say that if you do push the limits at the time, these really were the limits of getting somewhere close to what is the gold standard, then you get indeed within error of the experimental enthalpic value. And then you can use umbrella sampling, as was done in this case, just a comparison between the semi-empirical potential energy surface and the free energy surface that also agrees quite well with what then the additional entropic barrier is. But so it's possible to do this, but as I said at the beginning in my introduction talk, I don't think this normally should be the aim of you need to push the methods ultimately to get really far. You need to be lucky that you've got the right structure and everything. And so it can be hard to get it spot on. And sometimes you read in a paper, oh, and this agrees really well with experiment. It might be that they've used a suboptimal method, but there is some error cancellation going on, and that made it great. So what is a much better proof of your method and your reaction indicating the right thing is if you can get the difference correct between one variant and another variant, or in this case, the example I just showed, the reaction in solution and in the enzyme. Okay, so there are some of these aspects in this review. I don't have to highlight that further. But what's also in this review is sort of some steps that you might want to take when you start your own Qmmm project. And first of all, that is the choice of the Qm method. Now, this is going to depend a little bit on what approach you want to take. Do you have the computational resources to do something at the DFT level? Also, what is the chemistry that you're interested in? So I've advocated that the use of semi-empirical methods can be really useful. But if you look at, say, a P450 enzyme, where you've got sort of a heme with an iron in it, then that's going to be useless. And you will need to use some level of DFT. Right, so the choice of NM force field is also something that can make a difference. And there aren't enough tests yet to say, oh, this MM force field is better for Qmmm reactions versus this. But it's something that is good to keep in the back of your mind. It's not the main thing that people will usually be thinking about in testing, but it can have an influence. What, of course, makes a difference is what you include in your Qm and in your MM region. So there are debates about this as well. Some people have said you need to make your Qm region larger and larger to actually be properly accurate. I think that's been disproven. That's not really necessary, but you do need to make sure that you include key electronic interactions as much as you can in your Qm region. Again, depending on what your goal is. You know, if you can probably afford to have a hydrogen bond that is not changing during your reaction across the Qm-MM boundary, especially if you're mostly interested in differences, so that that same error will be the case for your one enzyme variant and your other enzyme variant. Right, so then the type of simulation that we looked at today, both types, there can be sometimes reasons why you know, Qm-MM minimization doesn't work so well, and you just want to use the umbrella sampling type technique. One thing that can be useful if you use semi-empirical methods is to actually test if your semi-empirical methods get the mechanism approximately right. So is their transition state roughly the same as what you expect from a higher level method? You could do this on a very small model of your reaction without the whole enzyme being present, just the key parts of your system. And then there is always the choice of what software to use. So everyone will have their own preferences, like people have preferences for MD simulations. So there are lots of options out there for Qm-MM simulations as well. Traditionally, because it was the first program really to have any kind of reasonable Qm-MM interface, a lot of the Qm-MM work was done in Charm. If people have used Charm, the program itself, it's not user-friendly. The Charm GUI is user-friendly. Charm itself, not particularly. So Ember is what we use today. I think it's a very useful, user-friendly program, at least to start you off in a Qm-MM simulation. It has the further benefits that it also has some semi-empirical methods included internally, so you don't have to link to external Qm interfaces. And they've done that in a way that is quite computationally efficient. So that's what we've used today as well. We could actually do our umbrella sampling, albeit very short along the reaction, in 15 or so minutes. NAMD and GROMACS have more recently also included Qm-MM interfaces. I've got less experience with those. Generally, for enzyme reactions, there are also far fewer applications in the literature. It's even possible to do polarizable MM in a Qm-MM simulation. Again, that's quite advanced. And the one other thing that I really should mention here is that you can also run Qm-MM simulations within certain Qm packages. So if you come from the Qm side, people find that attractive sometimes. You know, if you know how to work with Orca or CP2K, you can do Qm-MM within those. You will then be needing something to set up your MM force field, but it's possible. You also have programs that effectively just deal with interfacing an MM program and a Qm program. There's a Python-based one, there's Pupil, which is quite old. And there is also Python-based ChemShell, which I'm sort of plugging here slightly because it's something that's developed in the UK, actually in the place where Sarah works. STFC has done pretty much all of the development of ChemShell, certainly PyChemShell, when it's moved to PyChemShell.
They have collaborators other places.
There are collaborators, and this will continue with collaborations elsewhere as well. I'm just mentioning that, so PyChemShell, I say here, can be especially useful if you want to, for example, use DFT calculations. There are other approaches as well, but just mentioning that because as we are doing tutorials, PyChemShell also has some material on how you would do this for a P450, so a heme-containing enzyme. And I think this is going to be extended with actual details on the reaction modeling for this same system as well. Okay, so I think that's my wrap-up talk. So